Okay, I'm going to get started. Last class we talked about charges as the source of electrical field. Today's class we're going to talk about charges as the source of electrical flux. So the electrical field from the last class and the electrical flux from this class are just two ways of visualizing, understanding how electrical forces between electrical charges work. So we're going to learn both how to understand it in terms of electrical fields and understand it in terms of electrical flux, because they're both very useful in problem solving and understanding electrical forces. I'm going to go through these three bullets here, three bullets. One is to introduce the concept or the idea and the definition of electrical flux. We'll do it in terms of its relation, its connection to electrical field. The second bullet is to introduce Gauss's law for electrical flux. It's the relationship between electrical flux and electrical charge, like Coulomb's law is a relationship between electrical field and electrical charge. So we'll introduce that. We'll look at some illustrations and examples of electrical flux, electrical field, and electrical charge to get used to the concept of electrical flux and its connection to electrical field and electrical charge. I want to point out that, if you're a biologist and you wanted to understand the electrical properties of a cell, and cells obviously have electrical properties, that's their key properties, you would use Gauss's law, that's this class, not Coulomb's law, last class, to understand the electrical properties of, for example, the cell or the membrane of the cell or an axon of a neuron. So it's very useful in that context, Gauss's law. Okay, concept of electric flux, definition of electric flux. Let's start there, if I can. So this slide is just to introduce conceptually three words that we're going to use in today's class, which are flux, that's one word, but also sources, another word, sinks, another word. Charges are sources and sinks of electrical flux. So as an analogy, think about this picture over here. So this is my kitchen at home. I took a photo of the sink. In this picture, we can see analogies to electrical flux, electrical sources of flux, sinks of flux, through sources of water and sinks of water and the flux of water. So over here, this is where the faucet is, and we can think of the faucet as a source of water. So the water is flowing out of the faucet. Down here, this is the drain. We can think of that as a sink of water. That's where the water is flowing into and disappearing. So the water is coming out of the faucet, that's the source. The water is going into the drain, that's the sink. And the flow of the water on the way from the faucet, the source, to the drain, the sink, that's the flux of water. So that's those three terms: source, sink, and flux. Here's a picture of the same terms in the context of electrical fields and electrical charges. So upstairs here I've got a positive charge. Downstairs here we've got a negative charge. Around the charges is an electrical field that we've mapped out with electrical field lines. We met this picture last class. I took it from last class. We can think of the positive charge as a source of electrical field, like we saw of the thought of the faucet as a source of water, or so it's a source of electrical field or electrical flux. We can think of the negative charge as kind of a drain for the electrical field or the electrical flux, like we thought of this drain as kind of the sink for the electrical field and for the water. So this is a sink for the electrical flux or electrical field. And then the lines of electrical field really represent the flow or flux of the electrical field in this arrangement of charges. So again, on left and right, we've got sources of water or electric field, we got sinks of water or electrical field and flux, and we got the flow of the water or the field. We've got the flux of the water or the field. These ideas of sources, sinks, and fluxes come up in all sorts of areas, actually. In economics, right, the production of goods, that's a source, and the consumption of goods, right, that's a sink for the goods. So it comes up there. In biology, ecology, right, the growth, right, that's a source, and the decay away, the decline of a population, that's the sink for a population. So it comes up in a lot of fields, a lot of different fields. Okay, wanted to make a little bit more technical point about flux versus field. So electrical field, when we think of the electrical field, we think of there being an electrical field at a given point. So when I think about the field, I'm thinking about at this point, what is the electrical field? When I think about flux, I think about the flux, electrical flux, through a surface. So I'm thinking about a surface and what is the flux through that surface. So that's depicted on here, right? Here's the arrangement of positive and negative charges again. Here I'm thinking about the field, this magenta arrow, at this particular point, its size and direction. Downstairs here, I'm thinking about flux. I've given it the symbol phi. I've given it subscript E for electric flux. I'm thinking about the flux through some surface. This olive rectangle represents some surface through which there is a flux of electrical field. A diagram of field lines, electric field lines, represents both the field and the flux, if you learn to think about it in the right way. So the diagram of electrical field lines tells us the electrical field by seeing how closely the field lines are packed and the direction of the field lines. So that's how we can spot the strength and the direction of the field up here. But the field lines also indicate the flux through a surface as well. All you have to do is count how many field lines pass through a surface, and that's a measure of the electrical flux. So there's 3 field lines through this surface. That's a measure of the flux through that surface. If there was 5 field lines, that would be more flux. If there was just 1 field line, that would be less flux. So we can visualize with the field lines both the electrical field at a point and also the electrical flux through a given surface. I don't know why I have so much trouble changing the slides, but anyway, getting even more quantitative now. Getting even more quantitative, I want to write down a formula for the electrical flux, and I'm writing down a formula for the electrical flux through a surface, and I'm relating it to the electrical field at the location of the surface. So we're defining the new thing, flux, in terms of the old thing, last class, field. That's this equation up here. This is going to be our definition of electrical flux, the phi E here, in terms of the field here, the E's here. This is a picture that goes along with the equation. This too kind of defines what we mean by the electrical flux in terms of the electrical field. So maybe we'll start with the picture and then we'll work up to the equation. On the picture, I've indicated several quantities. In orange are field lines representing the electrical field. So here's the electrical field E. In brown here, here's a surface. It has a certain size, number of square meters, number of square centimeters. It has a certain orientation, right? It seems to be standing upright, for example, and facing from the left to the right. I can represent the size and the orientation of this surface by this vector here in magenta. I called it A because it represents the area of the surface. It has a size that represents the number of square meters of the surface. It has, or square centimeters of the surface, and it has an orientation that represents the orientation of the surface. This vector here, by convention, it points perpendicular to the face of the surface. So that the surface is kind of like the palm of my hand here. And the vector A is pointing perpendicular to that. And so the orientation of the vector and the length of the vector are telling us about the surface, both the surface orientation and the surface size. So E and A are the two ingredients in computing the flux. Basically, the electric flux through that surface, due to the electrical field at the location of that surface, is basically the product of the field and the surface area. That determines the flux. Subtlety is it's the field perpendicular to the surface that contributes to the flux. So we write the flux through this surface as the product. You can write it this way. This is the product of the area of the surface times the perpendicular component of the field. Or you can write it as the field times the area, the strength of the field times the size of the area, times the cosine of the angle between the two vectors representing the electrical field and the area of the surface. So these are two ways that we can write the electrical flux. Basically, that equation, or those equations, combine both the fact that the flux depends on the field, it depends on the area of the surface, but it also depends on the relative orientation of the field and the surface. And we'll see this, how this works out in a couple of examples in a moment. The units of flux are easy for us to figure out because we know the units of the ingredients in the flux. The units of field are newtons per coulomb. The units of area are meter squared, so the units of electric flux are Newton meter squared per coulomb. So those are the units. To get a better idea of this definition of flux, because kind of now it's a little bit abstract, let's look at an example. I think I'm going to do that next, but I'll never get there. Okay. I got 3 slides that are going to look like this. These 3 slides are to examine or explain or illustrate the dependence of the flux on the area of the surface, it depends on that, on the size of the electrical field, it depends on that, and thirdly on the relative orientation of the field and the surface. So those are the 3 things that flux depends on. And I'm going to go through these pretty quickly because on each slide it's kind of the same picture of surfaces in fields, surfaces with different sizes or surfaces with different orientations or surfaces in different strength fields. And I'm just comparing how the fluxes are through those surfaces. So this is Speedy Gonzales is an international symbol for, if you put it on the slide, you can go pretty fast on these slides. So this slide is to illustrate, this slide is to illustrate that flux depends on the area of the surface. So how am I illustrating that? Well, I'm imagining a uniform electrical field. That's the field lines in blue. They're the same everywhere. So that's a uniform electrical field. It's no stronger or weaker on the left or the right or the center. I'm imagining 3 surfaces immersed in that field. This surface over here on the left is relatively large, the one on the right is relatively small, the one in the center is somewhere in between. I'm calculating the flux through those 3 surfaces. Because the surfaces are perpendicular to the electrical field. The electrical field's all running left to right, and the surfaces are all standing vertically. So the two directions of the faces are perpendicular to one another. I'm just going to use this equation here for the size of the flux. The perpendicular electrical field times the area of the surface. And what you see is if you do the calculation of the flux through the large surface, you get a large flux because the surface was large. If you do the calculation of the flux through the small surface, you get a small flux because the surface is small. The field in each case, the perpendicular component of the field in each case was exactly the same. So this is the dependence on of flux on area of the surface. And it's kind of obvious. If you've got a big surface or a small surface in the same field, the big surface has a large flux through it, the small surface has a small flux through it. Another one that's obvious, if I ever get to it, is that the flux depends on the strength of the electrical field. So on this slide, right, I've got a electrical field that varies in strength from the left to the right. If you look over here, there's tightly packed field lines on the left, so there's strong electrical field. On the right, loosely packed field lines, so there's a weak electrical field. In the center right, some intermediate packing of electrical field lines, so that's some intermediate electrical field. In that field that varies from left to right, from strong to weak, I put a surface that we're going to figure out this flux through the surface. The surface in this case is the same size in each case. It's always the same size, always the same orientation. So this is a demonstration. This is a slide that describes the dependence of the flux on the electrical field. It's the only thing that's changing here. Again, I've calculated the flux downstairs here by this equation that says that flux is equal to the perpendicular component of the electrical field, perpendicular to the surface, times the area of the surface. In this case, all the areas are the same, but the field's bigger on the left, so the flux is bigger on the left. The field is smaller on the right, so the flux is smaller on the right. And the field is intermediate in the center, so the flux is intermediate in the center. So this just illustrates that flux also depends on the strength of the field, which is kind of an obvious thing too. Okay, final one. And this is the one that you can get caught out with, because flux also depends on the orientation of the surface in the field. And this illustrates that the flux depends on the orientation in the field. So this field here in blue is the same everywhere on the slide. So the field is a constant field. This surface in red here has the same size on the three surfaces. So it's exactly the same size surface, it's exactly the same size field, but it's not the same flux through the surfaces. It's very different fluxes through the surfaces because the orientation of the surfaces in the field, the relative orientation of field and surface are different in these particular cases. One way to that, not numerically, but conceptually, to see the different fluxes through these surfaces is to remember that the flux through a surface is in proportion to the number of lines, field lines, that pass through the surface. So that's a handy way of visualizing flux. So let's just walk through from left to center to right and think about the field lines that are passing through the surface and whether they're large or small. Right, this surface here. Well, if I count 1, 2, 3, 4, 5, 6, 7, 8. 8 field lines passing through that surface. So that's a relatively large flux on this picture. This surface here, remember, it's the same size, but it's orientated differently. Now it's horizontal. The field lines are running horizontal, and so think about it. None of the field lines pass through that surface. They either pass over the top of the surface or underneath the surface, but none cut through the surface. None go from below to above or above to below. So actually, in this case, there's no flux through this surface. There's zero flux. It is a surface in a field, but there's no flux through it. What about the one on the right? What's the flux through that surface? Well, the one on the right is neither simply vertical or neither simply horizontal. It's got some angle with respect to the electrical field. And we'll talk about the calculation in a moment. But let's first of all just count how many field lines pass through that surface. Well, 1, 2, 3, 4, 5, 6. So it has a flux through it, but the flux is less than this surface over here. Because we've reorientated that surface that was vertical, now away from vertical, that's changed the flux. So flux depends on the relative orientation of field and surface. If we wanted to calculate these three fluxes through these three surfaces, rather than just calculate the number of field lines, we could use this equation here. This was the second way that I wrote down the flux through a surface. And this way of writing down the flux through the surface is to use both the strength of the electrical field at the surface, the area of the surface, and the relative orientation of the field and the surface. And when we describe the relative orientation of field and surface, we use an angle theta, and that angle theta is the angle between two directions. One of the directions is the obvious one, the electrical field direction. The second one is this sometimes a bit of a trap, but the second one is the direction of that vector A that we use to describe the surface. So look, this is A here, this red arrow here, is pointing perpendicular to the surface. So like the field, it's pointing in the same direction towards the right. In the center here, this red arrow, this is the vector A that's pointing perpendicular to the surface. Its direction describes the orientation of the surface. Since the surface is now horizontal, it's tipped over and pointing downwards at 90 degrees to the face of this surface. And then here, this red arrow here, this represents the orientation of the surface in this case. And it's pointing, again, it's at 90 degrees to the surface, which makes it, we're told, at 30 degrees to the electrical field vector. So it's with these angles, 0 degrees between E and A, 90 degrees between E and A, and 30 degrees between E and A, that we compute the fluxes. And so that's, if you look at the equations here, the only difference between them, the E's are the same, the A's are the same. There's nothing different about size of the field, size of the surface. The only thing that's changing is the orientation. Cosine 0 degrees, cosine 90, cosine 30 degrees. And we plug those numbers in and we get numerically the fluxes. The largest flux on the left, the zero flux in the center, and some intermediate flux determined by this angle 30 degrees on the right-hand side. Okay, I hope that's fine. That's our definition of flux. Okay, I got two pictures because I just wanted to relax after all that. For me to relax, saying those words so quickly. So again, there's lots of analogies with flux. If you want to visualize flux, traffic flowing down a highway. That's kind of like an analogy of flux. So flux measures kind of the number of field lines through a surface, and you might measure the number of cars along a highway through across a line on the highway. So those are examples of flux. And the other picture I had to calm us down was flow of water through rivers and streams and estuaries, etc. Again, the analogy is that the flux of an electrical field is counting the number of field lines through a surface. Here we would be counting the amount of water through some surface through which the water is flowing. So there's lots of applications of flux and sinks and sources in all sorts of fields. Oh, I wanted to just show you one little, I wanted to ask you one question, just to check we all understand flux with this demo, right? So this little demonstration here has representations of field lines. So these arrows These are the field lines. So we're imagining an electrical field. And then it has two surfaces. There's this smaller surface here that's standing straight upright. And then there's this larger surface here, which is kind of angled. And the question I want to ask you is, which surface has the larger flux? Think about which one has the larger electric flux through the surface. Now, the answer is that they both have the same electrical flux through the surface, despite the fact that one is larger, one is smaller, despite the fact that they're orientated differently. For example, if you count the number of field lines that pass through the two surfaces, well, it's 9. There's 9 field lines here, and 9 field lines pass through this surface, the angled one, and 9 field lines pass through this back one, this other surface, this vertical one. So there's the same number of field lines through. So there's the same flux through these surfaces, despite the fact that the vertical one has a smaller area and the slanted one has a larger area. The vertical one is orientated at an angle of 0 degrees. It's vector with respect to the electrical field. The slanted one has a different angle that's not 0 degrees of its vector A with respect to the surface. And those two effects cancel out. One's larger area, one smaller area. They're two different orientations, but overall the same field lines are going through both surfaces. And so that's an illustration of electrical flux. Okay, I'm going to go on to another illustration that introduces a concept that surfaces can be closed surfaces or they can be open surfaces. So right now I just said the word surfaces. But actually we make a big distinction between open and closed surfaces, and so I want to say a few words about that. As an example of a open surface, okay, my laptop, I can think of that as a surface. This is an open surface. If I'm on the right-hand side of the laptop, I can just walk around to the left-hand side face of the laptop without having to walk through, smash through the laptop. So that's what we mean by an open surface. Supposing you had a soccer ball, right? It's not a soccer ball, but supposing we had some sort of ball. If you were inside the soccer ball, you could only get to the outside surface of the soccer ball by going through the surface. If you were outside the soccer ball, you could only get to the inside of the soccer ball by going through the surface. So that's what we call a closed surface. So a closed surface, if you're inside it, you have to go through the surface to get outside it. Open surface, there's really no meaning to inside or outside. You can just walk through from one face to walk around from one face to the other face. So closed surfaces that have a distinct inside and outside. Open surfaces don't have any distinct inside and outside. Well, in this sketch here, what we're going to do is calculate numerically the flux through a closed surface. So in the sketch, we're imagining an electrical field. So that in red are field lines. The field is kind of sweeping from left to right. It's meant to be in the x direction. There's x, y, and z directions here. So there's a uniform field, 500 newtons per coulomb, that's streaming from the left to the right in the positive x direction. Immersed in that electrical field is a closed surface. It's a closed cube. So that's a closed surface. If you were inside, if I put you inside the cube, You couldn't get out unless you bashed your way through the surface of the cube. If you were outside the cube, you couldn't get in unless you bashed your way through the surface of the cube. So we're going to calculate the flux through this cube, the electric flux through this cube. So it's a little bit of practice with electrical flux and surfaces and working with orientations of surfaces, but it's also actually going to lead us to an important discovery, and it's going to lead us ultimately to Gauss's law. So maybe I can do this, if I'm brave, on the document camera. So I started the problem here. Look, not a great drawing, but here's the cube. Here's the electrical field. I drew a couple of field lines. I wrote down a couple of numbers. Electrical field is 500 newtons per coulomb. The area, think of this, we're going to think of this, the cube as made up of 6 faces, right? That's how we're going to calculate the flux. We're going to calculate it through each of the 6 faces. And the area of each face, because it's a 1 centimeter by 1 centimeter by 1 centimeter cubed, is 1 centimeter times 1 centimeter. That's 1 centimeter squared. So this is the size of the area. Maybe I'll be more precise. This is the size of the electrical field and the size of the area. So what I'm going to do, rather painfully, is calculate 6 fluxes through the 6 surfaces, and then we're going to add up those fluxes to get the total flux through the surface. So let's see. Let's start with, I drew the top surface here. I hatched that in as an example. So let's start with the flux through, I'm going to put a little label on it, T for top. What's the flux through the top surface? Well, it's just going to be E A times the cosine of the angle between the electrical field vector, that's pointing from the left to the right, and the area vector, that's pointing upwards. They're at 90 degrees, so it's going to be cosine of 90 degrees. So we're going to compute that. At this point, I want to explain something. Why did I draw the area vector of the top surface? Why did I draw that up? Why didn't I draw the vector of the top surface down? Both of those are perpendicular to the top surface, which was the direction I described for the area vector A. But when you have a closed surface, this doesn't apply to an open surface. When you have a closed surface, there's a convention. You always draw the area vector pointing out of the surface rather than into the surface. So I'm obeying a physics convention. I'm obeying the physics convention that we're going to draw there's a choice about A, whether I can draw it pointing up or down, both the perpendicular surface. The convention is you draw it pointing out of the surface. And we always will draw it pointing out of the surface. So A was drawn pointing upwards. And as I say, it's 90 degrees to the field. Cosine of 90 degrees. Who knows what cosine of 90 degrees is? Well, it took me many years to understand that, but it's 0. Cosine of 90 degrees is 0, and so there's no flux. And you can see it, obviously. There's no field lines passing through that surface. Well, we could do the bottom surface next. That's down here. I could write EA cosine 90 degrees again. It's the same size E, it's the same size A. It's also 90 degrees to the surface, to the electrical field, so the angle is also 90 degrees. Everything's the same. The answer is the same. There's no flux through the bottom surface. Again, you can see no field lines passing through that surface. So there's going to be no flux through that surface. Look, there's a front surface. Now the picture's really getting screwed up, but there's a front surface to the cube, and there's also a back surface to the cube. So let me do those two also. Front Now I've got into trouble with my subscripts because I want to write back reverse. What's the flux through these two? Well, it's the same formula again, right? It's going to be EA cosine of the angle, cosine of 90 degrees again. You know, that front surface has a vector A that's pointing out of the screen towards you. That's at 90 degrees to the electrical field that's going from left to right. So again, there's no flux through that surface. You can see it because no field lines punch through that surface, go into or out of the cube through that surface. So that's also 0 degrees. And the same applies to the reverse, the back face. There's no field lines going through that surface. Everybody okay with all that? A lot of words, calculations about 0. There's no flux through the tops and the bottoms and the front and back. When we come to the left and right, it's a little bit different. Let's do right, and then let's do left. Same equation again. EA, E's the same strength, A's the same size for the front, from the left and right surfaces. But now, think about that area vector A. For the right-hand face, it's going to be pointing out the cube, so it's going to be pointing towards the right. So it's exactly in the direction of the vector E. So this will be cosine 0 degrees. For the left-hand face, this is the face over here, it's going to be pointing out of the cube, so towards the left. It's pointing in the direction opposite to E, so that's 180 degrees. Cosine of 0 is 1. Cosine of 180 is -1. So these two angles will give us a 1 and a -1, and if we fill in the numbers, the numbers were 500 newtons per coulomb for the field, is 10 to the -4 square meters for the surface areas. We get plus 0.05 newton meter squared per coulomb, and minus 0.05. There's flux, positive flux coming out on the right, and there's negative flux going in on the left. We've calculated all the 6 fluxes now through the 6 faces. What's the total flux through the cube? You just add up the fluxes for all the individual cases. If we add up all the fluxes, it's 0 plus 0 plus 0 plus 0 plus 0.05 minus 0.05. The total flux, I'll write it as a big letter here, is 0. There's no net flux through that cube, because as much flux goes in as comes out. In this case, it's going in through the left-hand face, and is coming out through the right-hand face. Overall, there's zero flux. Actually, it's interesting. We put a cube in a uniform electrical field, and we found there was no net flux through the cube. But actually, if you put any shape in a uniform field, maybe you put a sphere in there, or maybe you put a cylinder in there, or maybe you put some other shape in there. No matter what shape you put in there, if it's a uniform field, as much flux goes in as comes out. You could imagine every field line that goes in would come out, and therefore, for any shape, not just a cube, the flux, total flux through the surface in a uniform field is going to be 0. Okay, now go do Gauss's law.
Excuse me.
Yes.
How did you get 0.05 rather than 500?
I got 500 times, so the area was 1 square centimeter. Good question. I've got to put it in meters squared though. So 1 square centimeter is 10 to the -4 meters squared. So 10 to the -4 times 500. That's how I got that number. That's a good point to clarify that. Otherwise, it's kind of obscurely confusing. Okay, Gauss's flux law. So I'm moving on to Gauss's flux law. Gauss's law and field properties. Gauss's flux law, let me just, write it down and show you a picture of it, because that's where we're going to start from. It's, in a way, a very simple equation, and it's, in a way, kind of easy to picture, and that's what I put on this slide. So in words, Gauss's flux law, Gauss was a mathematician. They called him the Prince of Math because he was so famous as a mathematician, but he also did some physics. He did Gauss's flux law. Gauss's flux law says that the flux through a closed surface, so like the cube we just talked about, or like the soccer ball we talked about, flux through a closed surface is proportional to the charge inside the closed surface. So you could imagine some charge inside, that contributes to the flux. If there was charge outside, that actually doesn't contribute to the flux. So it's really an interesting law. The flux through any closed surface, no matter the shape, nice cube, nice sphere, some funny blob, whatever the shape, the flux through the blob or the sphere or the cube is equal to the proportional to the charge inside the closed surface. The proportionality constant. What's the proportionality constant? I lost the pointer. That's written down in this mathematical expression of Gauss's flux law. So here's the flux through a closed surface. Here's the charge inside the closed surface. So I put E subscript here for electric flux. I put in subscript for the charge inside. And the coefficient of proportionality, we can write it this way. This is the Coulomb constant. So you can write that coefficient of proportionality is 4 pi times the Coulomb constant that we're familiar with. Or you can write it in terms of another constant. I'm introducing this for the first time. It's the charge divided by the electric permittivity. So there are just two different ways that we sometimes write Gauss's flux law. They're both equivalent. They both use constants of nature. The two constants of nature are related to one another. K is 1 over 4 pi epsilon naught. So the Coulomb constant equals 1 over 4 pi times the electric permittivity. They both characterize how strong or weak electricity is. They're just numbers that characterize that, and sometimes it's handier to use one, sometimes it's handier to use the other one. And Coulomb constant is handier in Coulomb's law because it makes the law look simpler. Electric permittivity is in a way handier in Gauss's law because the law is simpler in terms of the pointer's not working for me, but it looks simpler in terms of the electric permittivity. But either is fine, whatever your personal preference, I would say. The picture is a visualization of Gauss's law. We got a surface. This one is kind of a blob. Remember, this is a two-dimensional depiction of a three-dimensional surface. We're imagining this charge is within that surface and creating electrical field lines and electrical flux through that surface. And Gauss's law just says that the flux of these field lines through that surface is equal to the charge inside that surface multiplied by 4 pi Coulomb constant or divided by electric permittivity of free space. So either way. So that's a picture of Gauss's law. I think it's really a wonderful law. Actually, it's really a wonderful law and what you can use it for. And we'll see that. Okay, here's a way of visualizing it. Lady Gaga came to last class. I'm actually a member of the Lady Gaga fan club. And part of it is she often has very interesting and important things to say, at least to me. Imagine sheep were electric charges. So here's a sheep, and here's another sheep, and we're imagining these are electric charges. One is inside a closed surface, and one is outside a closed surface. So this is the sheep in, and this is the sheep out, and they create sheep field lines, and they create sheep flux, and the sheep flux through the closed surface here, the pen, is entirely determined by the sheep that's inside the closed surface and completely irrelevant in terms of the total flux through the pen is the sheep outside the closed surface. So if you've got a charge inside the closed surface, that contributes to the flux through the closed surface. If you've got a charge outside a closed surface, that doesn't contribute to the net flux through the closed surface. Here's another example that illustrates that, you know, we've talked about Gauss's law now for describing electrical flux, Coulomb's law for describing electrical field. The two of them are actually related. They're really like relatives. They're like your aunt and uncle or something. They're connected together. And this just illustrates, this slide just illustrates that. So I'm thinking about a charge here. It creates an electrical field surrounding the charge. We picture that as field lines. It's a source of electrical flux. We've discussed that. And I'm picturing the electrical flux through this surface here, this spherical surface surrounding the charge. So the field strength I'm picturing by how closely packed the field lines are and the direction of the field lines. The flux I'm picturing through the surface by picturing the number of, imagining the number of field lines that are cutting the surface. So again, this is how we visualize field, how we visualize flux, how we visualize field at points, how we visualize flux through surfaces. How are the two related? How are these two things related? Well, let's start with calculating the flux through this closed surface here. So another example, another illustration of calculating flux. Remember, it's E times A. E is the strength of the field, A is the area of the surface, and theta is the cosine theta. That's the cosine of the angle between the field and the surface. So we just need to fill in those three things for this flux calculation. In this case, the field at this location on this surface of radius r, distance r from the positive charge, that's given by Coulomb's law. So this is Coulomb's law's expression for the strength of the field. I'm just plugging that in. The area in this case is the surface area of the sphere. Well, if you remember your high school geometry, the surface area of a sphere is 4 pi r squared. R is the radius. 4 pi r squared is the number of square centimeters, square meters of the surface. So I plugged in the area. What about the angle? Well, first that may look a little bit different because the field lines are going in all sorts of different directions and the surface is a spherical surface. How am I going to figure out the angle? But actually, if you think about it, everywhere E and the vector A at any point, they're both pointing outwards, away from the positive charge. So everywhere E and A is in the same direction. Over here on the left, E and A are towards the left. Over here on the right, E and A towards the right. Over here upstairs, E and A are upstairs, pointing up. And so the angle is actually 0 degrees. We've got, which is cosine of 0 degrees is 1. So I plugged in Coulomb's law. I can cancel out in the numerator and the denominator the r squareds. And if I do that, I get Gauss's law. So this is just to show you on a picture of a single positive charge, calculating the flux through a sphere around the single positive charge, that the equation for the electrical field, Coulomb's law, the equation for the electrical flux, Gauss's law, are just intimately related to one another. They're aunt and uncle. They're tied together like that. They're just alternative ways of describing how electricity works, and sometimes one is more useful and handier, like for the dipole, you want to use Coulomb's law. Sometimes another one is handier. If you had a sphere of charge, Gauss's law is way better. You want to use Gauss's law. Examples of Gauss's law. So now we've got to do some examples of Gauss's law. Qualitative example. Let's do this one. In this picture, we've got our point charge again, positive point charge in the center of the screen. It creates around it an electrical field. I'm showing the field lines. The field's strong near the charge and gets weaker far from the charge. The field points radially outwards from the positive charge. We're imagining three surfaces that are immersed in this field of this charge. There's this surface, I labeled it number 1, is this a horseshoe-shaped surface. There's this surface over here, spherical-shaped surface. I labeled it number 2. And there's this third surface down here, rectangular-shaped surface. I labeled it number 3. Now again, this is a two-dimensional depiction of three-dimensional field that goes in all directions and three-dimensional surfaces. So we have to be careful with that. I'm just trying to picture in 2 dimensions a spherical three-dimensional surface, a rectangular box-like surface, and some horseshoe-shaped surface. So these are three-dimensional surfaces in a three-dimensional field. And the question asks us to compare the flux, electric flux, through these three surfaces. So let's think if we can compare the electrical flux through these three surfaces. Well, Gauss's law told us that the electric flux through a closed surface, these are all closed surfaces, is in proportion to the charge inside the closed surface. So to figure the flux and compare the flux through the three closed surfaces, we just got to compare the amount of charge inside the three closed surfaces. So let's go and look at the picture and see what is the charge inside the closed surface. How much charge is inside closed surface number 1? In the interior of it, there's no charge. This is like the sheep outside the pen. It's not inside the pen. There's no charge inside surface number 1, so there's no net flux through surface number 1. Surface number 2. Surface number 2, this charge is outside the pen, is outside surface number 2. So that there's no net flux through surface number 2 also, because we simply see there's no charge inside surface number 2. Surface number 3, this positive charge creating these field lines is outside of surface number 3. There's no charge in surface number 3, so there's actually no net flux through surface number 3 also. All of them have no net flux through them. Now, that's not to say they don't have field lines passing through them or flux going into and out of them. It's just that the total flux, the net flux, is 0. For example, look at this surface number 3. There is a field line that goes in, so that would be a negative flux heading into the surface at the top here, but it also comes out. So that's a positive flux coming out. And the sum of those two fluxes through the top and the bottom are going to cancel each other out. So it has flux in, has flux out, but the total flux, which is what Gauss's law is all about, is 0. The same is true for the sphere and also the horseshoe. This field line goes in, so there was a negative flux there, but it also comes out. So there's positive flux there that cancels out for the total flux. And every field line for the horseshoe, I won't count them all up, but every field line goes in on this surface downstairs here and comes out from this outer surface here. So there's flux going in and flux coming out. The net flux is 0. Time for a quiz, I think. Yeah, time for a quiz. So it's 10:24. I'll give you to 10:27. I believe I published it. this is also an arrangement of charge. This time it's a positive and a negative. It also has three surfaces, and the question is to compare the fluxes through these three surfaces that I labeled A, B, and C. So it's rather similar but not the same as the last question. It's based on Gauss's flux law and the charge inside a closed surface, like the last example. I'll say a few words about the quizzes. Okay, the quizzes, initially your scores will appear as 2 if you get it correct, and as 0 if you get it incorrect. I go in sometime afterwards, which is typically the weekend, and if you submitted your quiz in class, so at the time I see, but you got it wrong, I'll credit you 1 point. So actually you will get 2 points for a correct answer if you're here, 1 point for an incorrect answer. But I have to do that afterwards, and I typically do it at the weekend, so I play catch up. The other point is that, you can answer tonight the quiz if you wanted, but if you answer it tonight, I'm not going to give you any credit. So it may initially appear as 2 when you answer it, but again, because I'm going through it the weekend and looking at it, if you answered it half a day later, I'm going to credit you 0. So it has to be credited during the class period. Okay, I'll get started with the answer to this. So again, the key thing, if you want to compare the fluxes through the three surfaces A, B, and C, is to think about the charge that's contained in the surfaces, the net charge that's contained in the surfaces. And this one illustrates an important point. Charge A has a positive charge inside it, and so there will be a positive flux through A. So that is a non-zero positive flux. Surface B has the same positive charge inside it. It doesn't have the negative charge inside it. So surface B has that same flux as A passing through it. It's a different size. It's a different... the charge is located at a different place, but A and B actually have exactly the same flux, net flux, passing through their surfaces, and they're both positive fluxes because the charges inside them are both that same positive charge. Surface C, on the other hand, this kind of ellipse here, or oval here, that contains the positive charge and the negative charge. So what happens then? Flux is determined by a total charge. We got a plus Q and a minus Q. The total Q inside surface C is actually 0. It's a 1 unit of charge minus a negative unit of that charge. That adds up to 0. So there's actually net flux through that surface. If you were to count the field lines for the three surfaces, I won't do it right now, you would see that you've got net field lines coming out from A and B, and the same number of field lines if you total them up. But for C, you've got as many field lines going in as coming out, and so that corresponds to 0 net flux through that surface. Is that okay with everybody? So it's a good illustration of Gauss's law and this relation between charge and flux. Let's move on. I got 2 more examples I really want to get to. This one I'm going to do really quick. So this just asks us to use Gauss's law numerically this time to calculate the flux through a closed surface. We got a charge, and that charge is here, positive charge, inside a closed surface. This looks like a pyramid, but here I'm being told it's not really a pyramid. This is a tetrahedron. A tetrahedron is a geometrical shape that's made of 4 equilateral triangles put together in a three-dimensional shape. So it has 4 faces made out of 4, did I say 3 or 4? 4 equilateral faces, equilateral triangles. So that's not a pyramid, but it looks like, to a non-expert, a pyramid. Anyway, we got a 1.6 nanocoulomb charge inside that tetrahedron, and we want to find the flux through the entire tetrahedron, pyramid, and the flux through the individual faces of the pyramid, or tetrahedron. I want to do this on document camera quickly. So we're going to solve this with Gauss's law and just an idea of symmetry or geometry. So, and the numerical solution is quick. So Gauss's law, if you remember, said that the total flux through a closed surface is 4 pi Coulomb constant times the charge inside. The charge inside is 1.6 nanocoulombs. We can just plug in 1.6 nanocoulombs for Q here. Coulomb constant, 9 times 10 to the 9 Newton meter squared per Coulomb squared here, multiplied by 4 pi. I won't write in all those numbers because I'm really anxious right now because I've got to get to a final example. And so I'm not going to put in the numbers. I'm just going to tell you, if I plug in 9 times 10 to the 9 and plug in 1.6 times 10 to the minus 9, so it's really 9 times 1.6, because the 10 to the 9 and 10 to the minus 9 cancel out, you get 181 Newton meter squared per Coulomb. So that's the flux. Imagine trying to do this problem with electrical field and calculating the flux from the electrical field. It would literally take us the rest of the year. It'd take us the rest of the year because the shape, the tetrahedron, the field is different everywhere over the surface of the tetrahedron, and it's different in size, it's different in orientation. We'd never be able to calculate the flux from the field, but calculate the flux from the charge in Gauss's law, easy, straightforward. We did it in one line. What about the flux through the 4 surfaces? So I call those the sides, for lack of a technical word. How are we going to calculate that? Well, this is where symmetry comes in. This is where geometry comes in. Gauss's law is often connected to symmetry and geometry. You see, we got 4 faces. The charge is at the center. The charge is equidistant from every face. From every face, the charge looks the same distance away, so every face has the same flux through it. So if the total flux is 181 Newton meter squared per Coulomb, the flux through the 4 sides, the bottom triangle, and then the left and the right and the back triangle, they're all the same. They share it equally because they're all arranged symmetrically around that single positive charge at the center of the pyramid. And so we just got to take the total flux, divide by the number of faces. There's 4 faces. This comes out to be 45 Newton meter squared per Coulomb. Okay. Look how easy Gauss's law made this. As I say, if you tried to do it with Coulomb's law in an exam, you would never finish the exam. You've got to do this one with Gauss's law, and it makes it very straightforward and simple. Any questions on all that? Okay. Want to talk about just one slide about a little bit about conductors, a remark about insulators, and then look at an example involving conductors, insulators, and Gauss's law, and electrical charges, and electrical fluxes, and electrical fields. So I want to introduce a rule about fields and charges. I want to introduce a rule about fields and charges and fluxes for conductors. So this is the slide on the rule, and then we'll look at the example. Firstly, this is a rule that applies to conductors in equilibrium. Doesn't apply to conductors not in equilibrium. By equilibrium, I mean, remember conductors are filled with charges that can move around. Equilibrium means that, well, they may have moved around, but now they're just settled down. They're not, you know, flowing around the conductor now. Non-equilibrium was when the charges are still moving around. Say moving along a wire, for example, or moving through a fluid. So that would be non-equilibrium. These rules apply to equilibrium, not non-equilibrium. So that's the first point. Inside a conductor that's in equilibrium, firstly, rule number one is that the electrical field is everywhere inside the volume of the conductor. So maybe that conductor is a metal, or maybe it's salt water. Everywhere inside is going to be zero. The electric field is going to be zero. So that's a rule for conductors in equilibrium. Electrical field at the surface of the conductor, at the surface of the wire, or maybe at the surface of the fluids. At the surface of the fluid or at the surface of a wire, at the surface of the conductor, there can be an electrical field right at the surface, but it always points perpendicular to the surface, right angles to the surface. So the electrical field lines are always right angles to the surface of a conductor, like a metal or like a fluid, or like salt water. And finally, any net charge inside a conductor. You know, if there's a net positive charge in the conductor, in the metal, if there's a net negative charge in the conductor or the metal, then that net negative charge or positive charge always resides not inside the body of the conductor, the volume of the conductor, but on the surface of the conductor. It's sitting on the surface, and it's the source or the sink of those field lines that emerge perpendicular to the surface or head into the surface perpendicular to the surface. So these are rules for conductors. They don't apply to insulators. In insulators, you can have electrical fields within the volume. That's perfectly fine. You can have charges within inside the volume. That's perfectly fine, because in insulators, those charges can't move around. So fields can exist in the insulator, and charges can exist inside the body of the insulator. Okay. What am I doing? Don't know. Want to look at an example. Of Gauss's law, conductors, insulators. So here's the example. Who's a biology major in here? I mean, not that I am. Okay, so a fair number of biology majors. So this is an example from biology, really. It's the electrical fields, electrical charges of a cell. How do we figure out, you know, a cell is an electrical thing. How do we figure out the electrical properties of a cell? Well, we do it with Gauss's law. So you use Gauss's law if you want the electrical properties of the membrane of a cell, the cell as a whole, or you want, say, you're interested in an axon. What is the electrical properties of it? You would be using Gauss's law. So it's a good application, biology for Gauss's law. In this case, I've got a spherical cell. And in this spherical cell, here's the cell membrane. Of course, this is very thin. It's made of fat or whatever it is. And there's fluid inside and outside the cell. And those cellular fluids are made of ions. And so they're conductors. So it's a spherical conductor followed by a insulating shell, followed by a vat of another conducting fluid. So that's the arrangement of a cell. And you know, those conductors there are some sort of salt water with positive ions and negative ions. In this case, we're told that the intracellular fluid, so the fluid inside here, has a net charge that's plus Q. So it's got more positive ions than negative ions in the fluid inside the cell, inside the membrane. And based on that, we're going to figure out what the field looks like inside the cell, in the fluid inside the cell, outside the cell, in the fluid outside the cell, and what the field looks like inside the membrane, and where these charges are located in the fluid inside the cell and also in the fluid outside the cell. We're going to figure all that out. So a bit of biology, but with Gauss's, we're going to use Gauss's law. We're going to use our rules about insulators and conductors, because we've got insulators and conductors here, and we're going to use a little bit of geometry symmetry, because we've got I have imagined a perfectly spherical cell. Okay, so there's going to be 3 slides that are 3 steps. No real calculations or equations, well, one tiny one, but let's walk through them. Well, what was the first rule about conductors? First rule about a conductor is that there is in equilibrium. So we imagine this cell is in equilibrium. In equilibrium, there's no electrical field inside the volume of a conductor. So this salt water inside the cell membrane, it is a conductor. It is charged. But inside, the rule is that inside here, the electrical field has got to be 0. So if you were to swim around in here, then 0 electrical field everywhere inside the volume. Outside, this is also outside the membrane. This is also a conductor. If you swim around outside the membrane, it's a conductor. It's full of ions that have charges. But outside, the electrical field is also 0. So that's the application of the first rule about conductors, and it's told us that we might not have expected this because we're told that the conductor inside is charged, but actually the fields inside the intracellular fluid and extracellular fluid are actually 0. That charge in the intracellular fluid, the fluid inside the membrane, it must be somewhere. Rules of conductors say it can't be inside the volume of the conductor. It has to be on the surface of the conductor. So from the second rule, I think, of conductors, right, the electrical field is 0 inside here from the first rule. The second rule is going to tell us that the charge of this conducting intracellular fluid is going to be actually located on kind of the surface of that sphere of intracellular fluid. So I've indicated here in red, this is kind of the surface of the fluid, and all that positive charge is going to be spread out over this inner spherical surface. It's going to be spread out because of the symmetry. It's going to be spread out uniformly. So there's positive charges on the left and the right, upstairs and downstairs. Those positive charges would create electrical fields, right? And those field lines can't go into the interior because there's no field there, so they have to stream outwards. Outwards to the left, outwards to the right, outwards up, and outwards down. But they're not allowed to go into the extracellular fluid. Outside here, in the other conductor, outside the membrane, there's no field there also. So every field line that begins on a positive charge here, this is a source of field lines, must be terminated by a negative charge from the extracellular fluid immediately outside the membrane. So actually, there's positive charge layered on the inside of the membrane from the intracellular fluid, and then there's negative charge that's layered on the outside from the extracellular fluid. So that's an amazing thing about the cell, is that with net charge inside, it's all located on the inner wall of the membrane, and then there's an opposite amount of charge that appears on the outer wall of the membrane, and we've got that from understanding flux and Gauss's law and so forth. One more slide. What is the field inside the membrane? Because I didn't answer that. The field inside the membrane, remember that's a insulator, that can have an electrical field. The field inside the membrane is non-zero. These field lines that start on the positive charges and end on the negative charges, they're streaming through the membrane. They're passing through the membrane. So the membrane is a region of electrical field, which would exert electrical forces on electrical charges. We can figure out that field